Hello and welcome again, viewers, to another Tutor Wizard stream. This time we're doing History of Math. All right, Adrian, take it away.
Couched in there, I, as a mathematician, don't know how to do the history of math very well because I'm not interested in some of the problems like did we actually do that or did what was the exact date when they did those types of things. I just want to pull from all of the cultures of the history of our species and show us where we get what most people have to work with in the modern day, this symbol R, which is all the real numbers and the different kinds of real numbers. So quickly, as a real quick synopsis for that, let's talk about, we have the positive integers, which is just the whole numbers, 1, 2, 3, etc. Then the natural numbers just add 0. We get the epiphany that there's a symbol for nothing. Then we get die ganze Zahlen, which is the integers. They're using Z because in German Zahlen is integer. So then we get negative 1, 0, 1, 2, dot, dot, dot. We have ellipses in both directions. Then we get quotients of numbers, and we change them from quotients to calling them rational. So this is whole numbers. This is natural. This is integer. This is rational. It used to be quotients. What are they? M over n, such that m is in z and n is in z plus. That eliminates division by 0. Rational. And then we have, they didn't even give it a new symbol. They gave it the complement of the rational numbers inside R. So R is the disjoint union of all rationals and irrationals. This one is numbers that can't be written. R can never be written as m over n, such that m is in z and n is in z. It doesn't matter whether you're dividing by 0. There's numbers that you can't write as the ratio of any of these guys. Square root of 2 is 1. Pi is 1, etc., etc. Where are they getting these from? The golden ratio is 1. And this is what I wanted to start talking about. Sine of pi over 4 is 1, etc., etc. Where are they getting these things from? All of these things, when I write them down and see it, I see geometry in every single one of these descriptions. And you probably don't, and that's why I wanted today to do that, because I did it in my class the other day in Calculus 114. But I need to make a connection between this. So first of all, the easiest way to see this and connect to what I was just talking about, the Egyptians really liked the rational numbers and they didn't like the irrational numbers. But they, on top of this, didn't like the fact that they had infinite repeating decimal expansions. So they were trying to find the truncated ones and these unit fractions, etc. So this means that you have a repeating decimal expansion. And this one's a non-repeating. So the most intuitive way to think about the real numbers, not axiomatically through Dedekind cuts or Cauchy sequences, to show that there's no holes in the continuum and that there's a one-to-one correspondence between every number in this set R to matching it to number on the real number line. What do you do with this? You start going and you'd say, okay, we put positive integers this direction, and then the negative is a myth, you go left of 0, and so then you would go that way, and then where do fractions go? Oh, we start putting them in there, and then I want to put 3 over 2 here. I said 2. And then eventually we want to get these irrational numbers. Where does he go on this line? He goes right here. Square root of 2 is 1.414, 213, dot, dot, dot. And where's the golden ratio? The golden ratio is 1.6. So phi is going to go here, and then pi is a little bit more than 3. We're going to find out. But where are we getting these numbers from? Root and phi and pi. We're just getting them to just torture. I always say torture first year students. No, this is a good application, but it's not why I'm doing it. It's not my motivating factor. I want to figure out, and the reason why these numbers, especially this one, becomes so mystifying is you don't see the original problems that they were doing to discover such a number. And then you're just given these numbers. There's these numbers which are irrational and they have an infinite non-repeating decimal expansion, and it comes out of a vacuum, it seems, but it doesn't come out of a vacuum. It comes out of geometry every time. And so do the axioms of the real numbers. So once I have those real numbers, I also have properties like this, properties of the real numbers. A times B plus C is equal to A times B plus A times C. And that was the question asked while I was at the coffeeing hole getting more coffee for turning. That's one of the ones that goes into our
The
book of
coughing hole.
yeah, that's what I
Noting
call
it
it.
right now.
Yeah, because I say it all the time. It's like, why do they put me in building 9 when the coffeeing hole is in building 5? Do they not want this efficient? It's like, so as I'm at the coffeeing hole and re-coffeeing up, they're asking me, well, how did they come to this conclusion? How do they know this? And so what it is it's geometry. What you don't see is this is area. I have one side which is B plus C. And I have one side which is A. And so what's the area of the whole thing? The area of the whole thing is going to be this guy, A times B plus C. But then if I ignore this guy, what's the area of this? AB. What's the area of this guy? AC. Oh, so if I see that the whole thing is A times B plus C, that has to equal the area AB plus the area AC. So even the algebra that you're getting, the algebra is coming, it's coming from a geometric picture. Start linking these things. It gets a whole lot easier to picture in your mind and believe yourself that these are going to work when it's couched in areas. The other thing was that, okay, so let's segue into the next one. And then I'll show you where the numbers come from. I didn't forget. But the next one would be, it's in the title and no one even asks why it's called that. And so this is what I started saying, and then this is what I started realizing. Why do they call it sinus? We're going to get into that one too. That means bosom of address. In Arabic. Cats are messing. Did anyone else hear that? Cats are messing stuff. Cats are messing stuff up there. But you want to go direct if you're trying to understand something in mathematics, or why they call it matrix, etc., which means womb. You want to go to the source and see what the heck they were doing and what the first people were doing when they wanted to define such a mathematical concept. So in this, you've been doing this from grade school. Complete the square. It tells you literally what they're doing in the problem, but then they're going to say this: algebra plus bx plus b squared over 4 equals x plus b over 2 squared. And everyone nods and they're like, good. But why did they call this algebraic thing completion of squares? And you don't see, just like I did with the other ones, that these are geometric configurations. First of all, that's why they call it x times x squared, because this guy and this guy and this guy are all going to represent areas. These are all squares. This one is not a square. So how many squares are in this picture that I'm about to draw? Here's the first square. We can get into how to actually use compass and straight edge. I'm going to have to steal that whiteboard compass that Mark Solomonovich has, and then we're going to use my straight edge
Yes,
and
do
my
it.
compass.
Do it. Steal
Yeah,
it.
I'm going to take it. Speaking of which, we have to do non-Euclidean geometry later today, but we'll do this. Yeah.
Very good.
So now I'm going to cut this up. This is going to be b over 2. This is going to be b over 2. This is x. This is x. So this term x is x squared, the area of that square. And then what's the area of each of these rectangles? This would be b over 2x, and this one would be b over 2x. But if I add them together, guess what I get? This term is these two guys, specifically. And then what do I need? And then what's the area of the whole square? Well, this whole side is x plus b over 2. So the area of the whole square is this guy, x plus b over 2 squared. And what do I need to complete the square? This square, which is going to have area what? B squared over 4. So now I've found, using a geometric picture, what I would need to complete the square. So what they're saying is, if you have these first two terms, an x squared term, which represents the area of a square, and a bx term, which represents the area of one or more rectangles, what do I need to complete it to get a new bigger square from that? And again, what they're probably doing, I'm not suspecting, this is where it's like, I'm just making, let's make, a wizard just made up the genesis of this. It's like, I'm just going to go based on logic, I'm going to guess that they had a building or something like that, and then they want to make it slightly bigger, and they want to make a new square building. So they're going to be like, well, okay, I'm just going to go out this far, and I'm going to just go out a b over 2 area, and then I'm just going to add to that, and then I'm going to have this area. And then so now to get the big square, what's it going to be? I just added that little extra b over 2. The b over 2 comes from algebra, not from what they were actually doing, I'm going to suspect. But once I do that and call it b over 2, then we're going to get exactly 2 rectangles and then another little square. So how many squares are in this picture? 3. 1, 2, 3. So then they look at it, and this is the way that you prove Pythagoras' theorem and a lot of things geometrically at first. You look at a geometric object and compute the area 2 ways. I'm computing the area 2 ways. One way is looking at the whole thing. The whole thing is a square with side x plus b over 2. So what would that be? The area of that whole square has to be x plus b over 2 squared, multiplied by itself. On the other hand, I would have this square and then these 2 rectangles that I put in there. So what's the area that I would need to complete the square? I would need to complete it by looking at the area of this thing, which is b over 2 times b over 2, which is b squared over 4. So then that gives me the idea of what I want. But I can't now, on top of completion of squares, the other problem is they always showed you that calculation and then you screwed it up because you just tried to add that into your equation, which is crazy. This is the picture of how it works. But in the real world, you won't be given that. What you're going to be given is x squared plus bx plus c. And now I want to complete the square algebraically. So I ignore c completely. And I look at this. And I go from this formula now. What do I need to complete the square? This guy. So what I'm going to do is, this is what you do. And that's crazy. So what I'm going to do is something less crazy. I'm going to add 0. Slightly less crazy. And then now this is, by my formula, what? The completed square. So now that piece, that's what I wanted, but this is what I had to add was 0, cleverly. So now I've got what I want in the equation, but I haven't changed anything in the equation. And that will complete the square. And then this one will be x plus b over 2 squared. And then what am I going to do? I'm going to do the other dirty trick, because now I need a 4. And I multiply by 4. And that'll be negative b squared plus 4 over c. The a is missing because I divided it out. The first rule of completion of squares is divide out by a and absorb it. But that's going to eventually give you exactly the quadratic formula if you keep going. But first of all, that's what I wanted to point out was completion of squares comes from completing squares. And then the algebra on top of it means that you always focused on the thing that you needed, but then you're like, then they didn't really explain very well what you need. This is a 2-step process. First, you use the formula and the picture you should draw for yourself, and then you can figure it out every time what you need, b squared over 4. But then I have to add it in as 0 because I can't just change the equation. So I want to add it in as 0, and then I can get the completed square. Good. So that was algebra on distribution rules and completion of squares algebra. But where do these actual numbers come from that we call irrational or incommensurable to lengths in geometric pictures? So what you would call root 2 being irrational, can you see that still? What you see as root 2 being irrational, I'm going to say this exact same statement is what? Something that you've never heard before, hopefully. Lorenzo has, Tim has, the wizards behind the curtain know this, but the average person doesn't. This is going to say that, I can say it in 2 ways. The diagonal in a unit square is incommensurable to the sides, to the unit sides. I don't know why the D wanted to be a G there, but my hand doesn't listen to my mouth. That was a kitty. Noodles. Well, no, you're Willa. Come here. Just wait, I'm calling in a cat. Kitty, 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 kitty.
Your cat speech, your meows are immortalized on Twitch and YouTube now. So don't forget, viewers, these lectures are going up on YouTube. I will post the link to the playlist on YouTube shortly at the end of this stream.
You do.
So you can hear Adrian meow as often as you like.
She comes just close enough so I can't grab her. Because she knows, I know, you tried to run. I know your psyche. There she is. Hi. Now you're being nice. You don't like being picked up. Me neither. Everyone's like, why are you holding the cat like that? I'm like, would you like it if there was giants that just came around and grabbed you and was like, let's snuggle on Twitch now? It's like, no, you wouldn't. So I feel your pain. I feel your pain. I wouldn't want giants grabbing me and snuggling. They probably wouldn't, but I wouldn't like it if they did. All right, let's draw a picture here. I have a square, and it has unit sides, and it has a diagonal. So the other way I could phrase this is the hypotenuse in an isosceles right triangle is incommensurable to either of its legs. Two, I said. Does it go there? Possession? Yes. Me fail English? That's impossible. I think that was correct. So these are the way that I see it in geometry, and then you just get this square root of 2 is irrational, which is the same statement. So let's get rid of, most of the time that I've derived it is using the right triangle. So this is what a right triangle is. Isosceles means that the legs are the same length, and we're going to call them unit isosceles. Just for the sake of simplicity, you can call it, oh, maybe we could do that there. Tim, it took me a really long time and you already forgot, but I found a way of an application of normalizing something. If I called it A, for all intents and purposes, it's just going to be root 2A will be the hypotenuse. So then for all intents, we'll do it later, but remember, for all intents and purposes, I'm going to normalize to 1.
Right on.
Yeah, there. That's how that works. Math is a twisted ball of yarn. I never know when I'm going to connect two of the ends together, so I just did.
You never know when the yarn will twitch.
Yeah. Twitch on Twitch. All right, so I'm going to call H the hypotenuse or the diagonal of the square or the hypotenuse of the right triangle. And what they're saying by incommensurable is, and that's why they've called it a unit length, whatever unit length you create, the Egyptians used a cubit, which is the length of a forearm plus a hand plus 2 fingers. I don't know why either, but I don't know what Imhotep was smoking before he starts going out there, but once we get, Imhotep, and he's building all these Egyptian, he was one of the main architects for building these pyramids. Once he defines what a unit is, it doesn't matter how he came to this cognomen conclusion, or do you know what a meter is? Here's what I would call a unit meter or a unit stick. But how do you know how long that is? And why is it called a unit? It doesn't matter. Once I have this arbitrary length, then I want to lay off arbitrary length and build things. And it would be really nice to mathematically and physically and everything else to have a unit amount of these, and I don't want to use fractions of it, just lay out 7 of them and make the building 7 meters wide or something like this for the doghouse. But what they're realizing is no matter what unit I use, I can never get a whole or integer amounts of that unit length laid off on the diagonal or the hypotenuse, and what we call that is incommensurable. Another way of saying this modern is the amount of work I do at McEwen is incommensurable to my pay. Which means my pay is irrational, if you get the joke. Whatever. All right. So why is root 2 irrational? First of all, let's use Pythagoras' theorem to see that the sum of the square of the hypotenuse is equal to the square of the legs. You also see square, square, square. And so this will be 1 squared plus 1 squared, which is, last time I checked, 2. And then what would I get? I would get that h is the positive, because lengths are positive, square root of 2. And then we want to know, is this irrational? Yes, it is. Did we prove this already? I'm not sure. I just want to point out that this is definitely not, we can do it on the next stream, but I do have to go visit my dad soon. And so I promised I would be done in half an hour. Now we're closing in on an hour or more. That's okay, math. Time flies when you're having fun doing math. So this one is not rational, it turns out. And I use reductio ad absurdum to prove this. But where did it come from is my point, from a geometric consideration. Also now, the golden ratio, which I did show you how to do, but I'm just going to pretend. There it is. What the golden ratio is, you take any line segment AB, and you cut it at a point C in my derivation, it's f, but because I needed a bunch of other points in actually geometrically constructing it with straight edge and compass. But what this says is, let's call this x, or they would say AC is x in our modern algebra. They didn't have the modern algebra, so they couldn't call it that. So they would call it the segment AC and the segment CB. And so CB is equal to, we're going to call it a unit length for all intents and purposes. And now what the definition of the golden ratio of, or what Euclid calls it, the extreme and mean ratio, is that AC over CB is equal to, or no, sorry, AC plus CB, which is the whole, watch it. I switched to a different kind of math, the Greeks, and they're like, you're talking about Egyptian. So the Egyptians just attacked me just a second. Willa's like, I know, you don't even know what root 2 is, Willa. Be quiet. And so the ratio of the whole thing, this would be AC plus CB. The ratio to the whole segment over the smaller segment, or the large segment, which is AC, that should exactly equal in one magic cut the large segment to the small segment, AC over CB. So that's the definition of the golden ratio. In modern algebra now, I would say that that's x plus 1 over x has to equal x over 1. And then I can make this into an algebraic equation, which we're going to tie back into what I just did last time now. Do you see? How do I solve this? I complete the square. I complete the square on this algebra consideration now. So let's do that. So now that I have the idea of the golden ratio, what I see is I have x squared minus x. What do I need? B is negative 1. Negative 1, I said. B over 2 is negative 1/2. B over 2 squared is 1/4. So now I know that I need 1/4, but I'm going to add 1/4 and subtract 1/4. And then what am I going to do? I notice that in this one, I'm going to multiply by 4 over 4, and this is the completed square. So now that is x minus 1/2 squared minus 5 over 4 equals 0. Why did we do this? Because I want to know what x is, and I need to solve for x, but I need a clever way of completing the square so that I can write it as, instead the problem was Francois Viette notices that he's got an x squared term and an x term, and he wants it written as a single term so he can complete solving for x. So now that I've completed the square, now I solve for x, and it turns out x is going to be what? X minus 1/2 to the squared is going to equal 5 over 4. I bring the 5 over 4 over. I do x minus 1/2 is going to be equal to plus or minus the square root of 5 over 2. The square root of 4 is 2. And then I get x is equal to 1/2 plus or minus root 5 over 2. The golden ratio is that largest root, 1 plus root 5 over 2. And then we realize that in that unit square also, so this is root 2, root 3, root 4 is an integer 2, root 5. This length right here is root 5. It's also irrational. When you take an irrational number and you add it to a rational number, this is still irrational. You can prove, these are going to be some problems we're going to give to students. Show that the sum of a rational number and an irrational number are always irrational. And then if you take an irrational number and multiply it by a rational number, that is also irrational. So I know that the golden ratio itself is specifically an irrational number. Where did it come from? Building a Nautilus shell and the golden spiral and the golden ratio, but I had to complete the square to algebraically solve for what it was. But this is an irrational number. It comes from a geometric consideration. Good. Now let's do one more, and then I'm going to go visit with the family. We're going to bring back the trigonometry, the consideration of three-sided objects, but there's also, oh no, we got to do two. Where does that your friend pi come from? And why do we know that one full revolution of a circle is 2 pi radians? Well, because I know the ratio, if I call this the circumference and then I look at the diameter, that's going to be r and r. There's 2 radii in the diameter, and the ratio to circumference of diameter, or 2r, is always equal to pi. This is how we define it. It turns out he's irrational. So then that means that the circumference is 2 pi r, And if the radius is 1 in the unit circle, we get that 1 full revolution is the circumference of that circle, which is 2 pi radians. This is how I get the conclusion of the fact that 1 full revolution is 2 pi radians, which equals 360 degrees. 360 degrees comes from the Babylonians liking the perfect numbers 6 and 60 in their base representation of numbers, and 6 times 60 gives you 360 degrees, which is 1 full revolution. If I split this into 6 and then 60 minutes of arc or seconds of arc, minutes first, then seconds, we get the connection between the Babylonian 360 degrees, which we still use, to the proper 2 pi radians inside a circle. Also, it gives you another irrational number. All right, that was the first circle. The other circle I wanted to do, which is much fancier, is, I need purple, oh, where's Lorenzo's ones? All right, let's do this first. Then I'm going to do the center is this one. And then I need this one. We'll keep yeah, I'll keep going with the other color then. That's where they intersect. And then I want this one. But half of it specifically. They're doing trigonometry wrong as far as I'm concerned. Mark will agree with me. But why am I saying that? Because nowadays we focus on, let's call this T or theta, I guess, theta. We focus on sine theta, cos theta, tan theta, which is wrong according to the original Sanskrit picture. What this means cosinus, the complement of sine. So he shouldn't be there. It should be secant. Secant is the first 3 trigonometric ratios which come directly from this picture. Who is it? I just put it down. Secant is this one. This length right here is secant of theta, it turns out. Just a second, then I'll get excited. This one is tan theta. And half of the chord, or ardha jiba, is sine theta. This one is sine theta. So first of all, a line that connects 2 points in a circle is called a chord or a chord. In Sanskrit, I believe this is ardha jiba. Half chord. It's half of a chord, which makes perfect sense when you look at it from the geometry of the picture of what they're doing and what they tried to call it. Unfortunately, this goes from Sanskrit. They start just calling it jiba, and then in Arabic, to go to Arabic, we get that Arabic is right to left and vowels are diachromatic arcs. They're just, it's these squiggles, and then vowels are just these things in there, turns out. And so they would shorthand and give it like this, but then when they wanted to put it back into our phonetic English looking words, or the Latin words, this was either jiab or jayab, and I can never remember which one is the real word. I'm going to go with this one. This one means bosom of a dress. And then when they come along in the 1100s with Latin, they get sinus. And sinus in English means bosom of dress. Oh, I don't know how to spell dress. There's not 2 E's in there. I had it right the first time. Bosom of a dress. I said bosom, and then I wrote bosom, and then I didn't know how to write anything else after I said bosom. Bosom of my Babylons. It wasn't the Babylons. So from the original picture, there's 3 trigonometric ratios. Sinus, which is half chord originally. Secant is secare is to cut in Latin. And tangere is to touch.
I don't think there's the accents, but yeah.
Okay. Yeah. Is the accents aren't there?
Yeah, there you go.
I want them to be.
No, you got the pen.
It's fine with me. Accuracy, we're being historically accurate. Lorenzo's the historian, I'm just the crazy mathematician. And then in there, you would have complements. Cosinus, cosecant, cotangent, which are the complements of whenever you have the angle, this is the angle. The complement is what they meant, was the other half of this in 180 degrees, or pi radians. So that's my rant on the difference between the modern way that we focus on sine, tan, and cosine, which are the more useful ones, but they're all sinusoidal, because if we look at the fact that cos of theta is just sine of pi over 2 minus theta, then cos is just a sine function. And if all the other ones are just ratios of sine and cosine, then they're all just described with one guy, sinus, which is half chord in the picture. So it also connects the geometry of right triangles to all of these 6 trigonometric ratios, which were lengths of certain things in here. The secant was the length of the guy that cut the circle. The length of this guy was the tangent, the one that touched the circle. And then this one was called half chord in the circle. And then cosine becomes this one. This one is cosine, and the complement of this, and then cosecant, etc. You can find them all in there, etc., etc. And then how can we come to the conclusion that sine of, say, pi over 4 radians or 45 degrees is irrational? This is 1 over root 2, which is the reciprocal of an irrational number, which you can show is also irrational. So root 2 is irrational, so 1 over root 2 is irrational. So this is also not a rational number. I think that was my point, is where do all these rational or weird type of number, I'm pretty sure that we're going to end now. What that meant was, what I wanted to show is you need to start to get even to flesh out the last kind of numbers, or to Cardano and Tartaglia, even at first, they didn't like the fact that this had no solution, because they didn't know if this was an area, how could you ever have this where the length of the side of some kind of rectangle or something would be -1. So they didn't like the fact, and they had to invent new numbers. So this is it's essentially how you can get, just from a simple algebraic equation talking about areas, of how you would try to get a new number called -1. I just have to have a number which would be, once I add it to 1, I would get 0. And this is how we get the notion of -1. And all you have to do is put a square on one of these guys, and you can get a new type of number. Ooh, do that, and then all of a sudden you have, that, and you get x is what? I. So this is where the new numbers are coming from. They're all still deriving them from, originally from a geometric consideration, and then developing the numbers from there. We won't do the complex ones for now, but we will do the negative ones and the irrational numbers. They're all coming from geometric ratios. Have a good Mother's Day, etc. We're out.
All right, thank you, everyone. I'm just going to post the link to the YouTube playlist for History of Math, where all these lectures will be posted. So be sure to check them out, and subscribe if you're not already subscribed. Join us on Discord. The link is earlier on in the chat. Yeah, all right, thank you, everyone. We'll see you next time.